Today we're going to explore how to connect potential and current. A battery creates a potential difference equal to its EMF rating. That's what the EMF is. It is that potential difference that drives the current in the circuit, as shown abstractly below. We have charge is lifted along the charge escalator from the negative to the positive terminal. The wire provides a path, and so the potential difference creates an electric field, which is inside the field, inside the wire, which pulls positive charges along it. The electric field pushes the charges through the wire. They go down to the negative terminal, and then the whole process repeats. Bump, 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 and then it can keep going. Keep in mind, of course, that we could, if this is a real wire, we would know that it's actually truly electrons that are moving, and so they would be pulled off the negative plate and move the wire this way and go up here and then be lowered on the charge escalator. But electrons moving to the right are the same as positive charges moving to the left. So it doesn't have any empirical effect, so we're going to stick with our conventional current, pretending that positive charges move. All right, let's say we took that setup and we swapped out the wire for a new one, and we noticed that the current was now greater than it had been. Compared to the original potential difference between the ends of the wire, what can we say about the new potential difference? Is it greater, less than, the same, or would you need more information? And if so, what? It will turn out to be the same. Remember that the potential difference across the wires has to be the potential difference of the battery, the EMF of the battery. And so we haven't changed the battery, so we can't change the potential difference across the wires. All right, that's summed up here, that delta V of the wire is delta V of the battery, or is the EMF. And this potential difference across the wire is what sets up the electric field and causes the currents to flow. So we are sometimes a little sloppy because we say, well, the battery creates a potential difference, and that's what drives the charge through, and that's fine. But what's really going on is that that potential difference is also a potential difference in the wire, and it's the electric field in the wire that moves the charges along. All right, we can imagine making several different modifications to the circuit, and we can conceive of what would happen. For instance, we could change the potential. We could stack batteries, right? If we add a second battery, then we have increased the potential. And so much like increasing the pressure in a hose, we get more current. And that's, I think, entirely unsurprising. We could change the size of the wire. We could make the wire longer. If we make the wire longer, then there's more path that the charges have to take, so there are more opportunities to bump off of the various fixed charges in the wire. Remember that we've got electrons. What's going on here is we've got some sort of nucleus, and then we're moving charge through, and sometimes they hit the charge, and they bounce around. If the wire is longer, there's more things to hit, so it's harder to push stuff through. This is kind of thinking about how harder it is to push things through a longer straw than a shorter straw, so that's not too surprising. If we make the wire wider, then the charge has more flexibility. If one charge bumps into a nucleus and gets stopped, other charges can flow off to the side and move around it. So it's easier for the charges to make their way, so there's more current in a thicker wire. You can think of this as sort of, what if you had to, run laps in a hallway? If the hallway is longer, then it's going to take more energy from you to run the lap. That's not surprising. But if we have a crowd of people and we're having them run sort of laps together, in a narrow field, they'll have to go slower. There'll have to be less transport per second of people past a given doorway, because otherwise they'll bump into each other. But if you put them in a wide hallway, then they can find a much higher pace and not worry about running into each other. And basically the same thing's happening here. We could also change what the wire is made of, the material the wire is made of, because different materials conduct differently. For instance, copper is a better conductor than iron. It's easier to move the electrons in copper than it is to move the electrons in iron. As such, there'll be more current in a copper wire because it's just easier for the charges to move out. So again, sort of thinking about having a fluid that's viscous would be a high resistance fluid, a one that's low conductivity, or something which is inviscid is like having copper, having a good conductor. We characterize all these things together by saying a wire has something called a resistance, a measure of how hard it is to push current through. And we can see that the resistance will depend on some of these factors we just talked about. We usually think of this experimentally. We apply a known voltage across a known resistance and we get some amount of current out. But actually, we use this instead to define the resistance. We say apply some known voltage to a wire, measure the current that comes out, and then compute that the resistance is the voltage difference across the wire divided by the current that you saw. The SI unit of resistance is called the ohm and is symbolized by the Greek letter omega, or, and I kid you not because that's why they picked it, the Greek letter omega, which is pronounced as ohm. Ega. And that's why it's called the ohm. Really, we're not that creative when we name things. While 1 ohm of resistance is not unreasonable, it is relatively small. Most applications we're going to run into will have resistance in the kilo ohm or maybe even the mega ohm range. Be careful. The resistance is not necessarily the slope of a voltage current plot. All right, we see a delta over something else and we're like, oh, it looks like a slope. And probably if we were starting today, that might be how we define resistance, but this was sort of done in the 1800s when calculus was relatively rare and people sort of worked directly. You can see the illustration here that I've just mocked up a voltage resistance plot like this, and the slope of the VI curve is of course the slope of the tangent. So at this point we would take a slope of the tangent and measure that. But that's not the resistance. The resistance is this value of the voltage divided by this value of the current. And so it turns out to be graphically the slope of this dashed line, the line connecting it to the origin, which are clearly different. It's smaller. In fact, it's about half. Our earlier exploration showed that the resistance of the wire depends on both its spatial properties and on some internal properties. We capture those intrinsic properties, the internal properties, in something called the resistivity of the wire, symbolized by the Greek letter rho. And although I can't swear to it, I'm guessing that rho is from resistance, same R type sound. Good conductors have low resistivity, and poor conductors have high resistivity. This is a property of their atomic structure, the material that makes them up. Resistivity is temperature dependent. As the wire gets hotter, the atomic centers execute larger vibrations, making them bigger targets for the electrons to bounce off. So resistivity tends to go up with temperature. The unit of resistivity is called the ohm meter. I'm not kidding you. This is not a thing that measures ohms, but rather an ohm times a meter, and is symbolized, therefore, as ohm times meter. And we'll see in a little bit why it has that unit and where that bizarreness is coming from. Your textbook likes to list charts. The author's very fond of tables. So here is a table of various resistivities, and although the scale of these, you can see resistivities tend to be smallish. Right? In metals, they tend to be in the 10 to the minus 8 range, which is tiny. But in tissue, blood or muscle or fat, they can be in the actual positive numbers. And water, pure water, is a very high resistivity. This is a little counterintuitive because TV has convinced you that if anyone gets near water with anything like electricity, they get shocked and die. And that's because they don't tend to be stepping into pure water. Pure water, good old H2O, is actually an incredibly poor conductor. But impurities in the water can end up being good conductors. And so typical water will be much better. Notice that even seawater versus pure water, which is not very impure, but seawater is almost 1,000,000 times more conductive. So, do you need to memorize these numbers? You don't. It's good to notice what they have, what their rough scale is, and to see that metals tend to be around the 10 to the minus 8, some handful of those. They put in here the difference between temperatures. All right, the odd units of resistivity come from the way we define it in relation to resistance. We say that if we have a wire of length L and cross-section A, oops, so there's our wire, we say that the resistance is defined as the length of the wire divided by the area of the wire times this constant rho. And so we get the ohm meter stuff. Honestly, this could have been defined differently. They could have, for instance, squared the L so as to make it dimensionless. But back in the early days, people were really sort of just doing taxonomy and didn't know. And we get this now, where there's ohm meters. This means that the resistivity is not itself a dimensionless property, but that's fine. All right. Notice that rho is a property of the type of material. In other words, all copper has the same resistivity. But R is specific to a particular wire made from that metal or whatever. All pieces of copper would have the same resistivity, but they each have their own R based on their physical dimensions. Pragmatically, it's generally quite easy to measure resistance. This turns out to be a relatively simple measurement to make, but resistance is exquisitely dependent on the material in question. This allows us to use resistance as a probe of physical properties. For instance, while water is a good insulator, impurities make it a conductor, and its resistivity strongly depends on the concentration of those impurities. So we might have here, this is a water monitoring system, where we have some battery attached to some meter, and then we let the water flow between two electrodes. We just put two electrodes in the water. And we want to know what happens to the current if the salinity of the water increases, if it gets saltier. Well, based on our earlier chart, we found that increasing salinity decreased the resistivity, which would decrease the resistance, and therefore increase the current. All right. A wire is connected to a battery carrying a certain current. The wire is disconnected and stretched, which increases the length but makes it thinner, and is then reattached to the battery. How does the new current compare to the previous one? So this is our, let's do this. Here is our original wire, and now we've made it thinner but longer. What's happened to the current? Well, making it longer makes the resistance go up. Making it thinner makes the resistance go up. And both of those things will tend to decrease the current.